everyone, and welcome to E-Day Live. My name is Madhu Saker, and I am so excited to be here this morning as one of your co-hosts. E-Day, or Engineers Day, is a celebration of curiosity and innovation. For the next 2 hours, we'll be bringing to you live exhibits, demonstrations, and follow-along activities to help connect you to the world of engineering. We're streaming to you live from the Innovation Center here on campus. The Innovation Center is our engineering student makerspace. It's equipped with CNC machines, 3D printers, laser cutters, and so much more. As engineering students, we are so fortunate to have the space to be creative and build projects for our classes. This year's virtual event is organized by the University of Kentucky College of Engineering and sponsored by Lexmark and Lockheed Martin. Here's a list of exhibits coming up in the first part of the show next. Lexmark, Thinking Out of the Box, Lockheed Martin, A Helping Robotic Hand, ukSociety of Women Engineers, Science with SWE, and Interdisciplinary Engineering Outreach presenting Sugarcoat It. Be sure to ask questions and engage with the presenters through the live chat feature. All right, it's time to get started. Let's kick off E-Day with our sponsor, Lexmark, and Thinking Outside of the Box.
Welcome to E-Day. My name is Jenny Campbell, and I'm here with
Jerry Smith,
Sam Rodas,
and we are all employees of Lexmark International, located here in Lexington, Kentucky. I'm a mechanical hardware engineer, and I graduated from the University of Kentucky in 2002 and 2006.
I'm a physicist, and I've been working for Lexmark for 24 years, creating heating solutions.
and I'm an electrical engineer. I graduated from the University of Kentucky in 1995.
All right, so let's get some business out of the way. Lexmark is recognized as a global leader in print hardware, services, solution, and security by many of technology industry's leading market analyst firms. That was a mouthful. Let's make this easier. Lexmark makes printers. We make lots of printers, and we're really good at it. We are a global company, and we sell printers all around the world. You can find printers in Australia, Brazil, Poland, the United States, China. It's a pretty interesting place to work. Many of you will probably be familiar with a printer. This is one of our smaller printers, and as you know, you put paper in the tray, you send it information, and then it gives you a printout. So this shows the difference between different types of printers or sizes that we can make. And so this is one of our smaller printers shown here. It's about 15 pounds, and this is one of our larger printers that can be up to 240 pounds. So what a printer is, basically, it gets communicated information. It takes a piece of paper, picks it, transfers it through the box, and then it gives you that printout right there. So there's lots of technology in a printer. Regardless of its shape, regardless of its size, it's all the same. So Lexmark has recently developed a department called Lexmark Ventures. Not Lexmark Adventures, which would be cool, but Lexmark Ventures. Ventures' responsibility is to take existing printer technology and then match it to opportunities outside the printing industry. So how do you make a printer into something that's not a printer? Let's look inside this box so we can think outside the box. Within a printer and within a box, there is a collection of different modules. And these modules are all created by teams of different engineers. So a printer takes mechanical engineers, take electrical engineers, material engineers, optical engineers, computer science engineers. They take all the engineers. And then each one of those engineers create a different module that has a different function that's all needed to create that printout that I showed. So if we go through some of the modules in a printer, you can see that we've got frames. And so this is basically the house of a printer. And so it holds all those modules in the same place, and it really protects the structural integrity of all those modules that has to get shipped from place to place all around the world. Printers have to run on power. And so you have a power supply, and this is actually what plugs into the wall, plugs into AC, an AC supply voltage. This printer has tons of motors and different kinds of sensors in there that need a different type of voltage to run it. And so this module right here is what transforms that to the appropriate supply voltages to run everything in our printer. You then have the brains of a printer. So you've got a controller card. And so this is where all of your different components plug in. And this has the firmware that controls the timing of all of those motors and all those sensors to help take your blank sheet of paper, your image or your information, communicate it to it, and provide that printout. So from there, you've got a print head. And so this has lasers in it. Need I say more? So this is actually what is drawing the image that you've communicated to it and what's going to put it on the sheet of paper. You then have toner. And so this is one of our larger toner cartridges. You can see that toner, I don't know if you can see that, but toner kind of looks like a really fine particle, like a powder. But this is actually plastic. And so this toner and the print head work together to draw your image onto a transfer belt. And so if you took this out during a printer process, you'd actually see an image drawn in there. And that's what your sheet of paper is going to touch up against to get your toner and your image to your sheet of paper. And so then you go to a fuser.
All right. Hello, everyone. So I'm going to talk about the fuser. And after the toner is put onto the page, transferred to the page, it goes through the fuser. If you can give me the paper. And so as the fuser comes through the paper, we call it a fuser because it heats the toner, the fine plastic particles, and it presses them into the page. And so you can imagine when you're 9 years old, and a 9-year-old's standing on top of the fuser, that's the amount of force that's pressing down between the two rollers that are in here. And then inside the fuser is a heater. And I'll be showing another heater in a moment, but the heater is mounted and there's a pressure member behind it. And so the heater and the rollers and a roller or a belt that goes around it presses onto the page. The heater heats up, and you can see this cross section as well. The roller, the heater, the pressure member, and this belt I'll talk about more in a minute. The heat heats up in about 1.5 seconds to 400 degrees Fahrenheit. So similar to what an oven might be set on to bake something. But rather than taking many minutes to heat up, it does so in only a few seconds. The heater itself in about 1.5 seconds, and the fuser rollers in about 4 seconds. And so as the paper comes through and the heat and pressure are applied, the plastic particles are melted and pressed firmly into the page and fixed on the page, and that's how you get a permanent print sample. So now I want to talk about the components, because that's, as we think out of the box, these come into play. So first of all, back to the heater. This is an example heater with blue glass printed on it. This is thick film printed. Resistors are printed, conductors are printed, and then glass is printed. And there is a temperature sensor welded on the back side. And so we're constantly measuring and adjusting the temperature as needed as paper comes through the fuser. I've already talked about belts, but quickly, this is a plastic tube, seamless plastic tube that's in one of our models. And it's a special high temperature plastic called polyimide. It's the thickness of a human hair, actually a little bit less than the thickness of your hair. We also have other belts, and they are made out of stainless steel, also the thickness of your hair. We apply rubber on some belts, and we also apply a coating or a sleeve that prevents the toner from sticking. And it's like a coating that would be similar in your skillets at home. The pressure roller can be large, or it can be smaller. It can be solid rubber, again with a sleeve, or it can be with a coating. The rubber can be a solid rubber, or it can be a type of foam rubber. So when we think about this type of heating technology, think about what it might be applied to do. So now let's think out of the box. One thing that such a heater could be applied two is a water faucet. This has a heater inside here, so it heats as water's coming in and gives rapid heating on demand. Another thing we might find that could come out of the printer is a heating solution for a cabin heater in an automobile. This would be under your hood and maybe behind the engine. Hard to see, but fluid comes in, is heated, and comes out. So a cabin heater. As we also think outside the box, another application could be a clothes iron. This is a travel iron, and there's heating elements behind here, and you can imagine the benefit of this heating and cooling very quickly. Another application might be, let's think outside the box a little bit further, an ice maker. Whether you realize it or not, an ice maker actually has a heater on the bottom, and it helps release the ice after it's being made. So quick heating and quick cooling has direct application to large appliances and modules within them like ice makers. Another application, let's think further outside the box, could be cooking utensils. And so rice cookers or other cookers, pressure cookers, all have heaters in the bottom that heat the pan. And so a quick heating and cooling solution would be great for cooking applications. But at this time, I think we'll go to a special application, thinking out of the box.
Thanks, Jerry. So one application that we came up with that we were thinking, so what kinds of tools need to heat quickly, but cool quickly also? So we reached in the box, and what we decided to come up with was a hair straightener, of all things. You might not think that a hair straightener is actually an advanced technological machine, but if you look at this one's very special. As Jerry talked about the belt materials, this one actually uses that belt material. It is effectively a small printer fuser held in your hand, but instead of melting toner to paper, it's straightening your hair. It's actually styling your hair because it actually works as a great curling iron as well. A traditional hair straightener has metal plates here, and so they put heaters behind the plates heat up, and they get extremely hot, and they're a little harder to control because there's a lot of thermal mass that holds heat, and when you put something on it, it dumps heat very quickly, so there's constantly controlling, trying to get to a consistent temperature. Whereas ours, if you hear the difference, there's very little thermal mass here. So as Jerry talked about, the thinness of this belt and the thinness of the heater. So this is actually an example of the heater that's in this unit. This is the ceramic heater. As Jerry said, it's thick film printed. It's very precisely controlled. And because it's so thin, we can heat it very quickly and it cools very quickly. So we thought we might have some advantage by reinventing and rethinking how this tool might be used. So we started out by going and talking to people. We asked people who use these every day, what do you like about your current curling or straightening iron? What don't you like about it? If you could reinvent it, what would it do? How would it be different? So we took the team of all the engineers that we talked about earlier, the mechanical engineers, design engineers, electrical engineers, firmware, software. We all came up with this concept and this idea and built this product. We took it in the field. We've been testing it with salons, with people who are using it every day, giving us feedback. We iterate. We redesign it. We rebuild it. I'm going to come up with this concept. So I'll show you some of the advantages of this one. So we wanted to take it, make it very simple, even though it's an advanced machine. There's a status light here. So when I turn this on, I'm going to turn it to its highest setting, and you'll see this light blink while it's heating up. And once it's at temperature, it'll be ready to go. So I've just turned it on. You see it blinking. So it should be ready to go in about 6 seconds. And there it is. So now the light's glowing, and I'm at temperature. So this is over 400 degrees inside here on the plate. But one of the advantages that we noticed as we built this is that I'm at 400 degrees inside, but on the outside I can grab it and hold it. And it doesn't get hot on the outside. I can put it right against my skin. So one of the advantages that we have versus this one is I could put it right against my scalp and get right against the root. So when people are straightening, they don't have to worry about burning themselves on the edges like they have on traditional. We've got a kind of an advanced interface here. We're actually setting temperature based on hair type instead of on temperature. So You can go on the lowest setting and it'll cool down. It's ready to go. Or back up on the highest setting. Anything else we want to cover on it? I mean, I think
I think
yeah.
that's good.
Okay. So this is actually a product that we're actually putting in the market today. We're selling it under a new brand called Selexio. It's built with Lexmark technology from the Lexmark Ventures group. And this, I can't think of a product that's more out of the box than making a hairstyler from core printer technologies.
So, in conclusion, who would have thought beauty products were created by engineers? Who would have thought that we could have taken printing technology and made a beauty product? Trying to decide if you want a career in engineering can be hard if you don't really know what box that you want to create. But if you think about the technology that can go in the box, that might be what really excites you. Also, you never know what your employer wants to do with their technology. So your background, your diversity, your experiences could really help your employer come up with a new product. So, in conclusion, thanks for listening or joining Lexmark today as we talk outside the box about technology that we can develop from printers. So,
Yes,
thank you.
Well, guys, that was an awesome presentation. I'm so excited to see that really awesome hair straightener. Not being able to burn yourself is definitely a really nice thing. But what do you think is the coolest thing that you've had the opportunity to build while you're at Lexmark?
I think for me, it is building this, taking the core printer technologies that we discussed. So we call these the nunchucks because this is actually what's the guts that's inside this. So you can kind of see how it fits in there. The printed circuit boards that with components on it, you guys have probably seen that kind of stuff before. But there's advanced control logic on here. It was actually so advanced that we've patented the algorithm, the code that runs the power management of the tools. But again, you can kind of see the similarities. It's a different shape, of course, but it's the same material set, same safety features that we put in the printer or in this device. And I think this is extremely cool. I mean, imagine your boss coming and say, just go invent something new. Take what we've got and just go do something completely different. Mm-hmm. And then you come back and say, okay, I've got this beauty product. And they say, all right, that's awesome, go do it.
Yeah, that sounds like a great opportunity. Can you tell me a little more about how you tested that and
yeah, absolutely.
Yeah.
Gary, you want to go?
So we created a robot, and we have hair extensions on the robot. And so if you can imagine, we mechanically close it, goes down the hair extension back. And we have tested hundreds and hundreds and hundreds of miles of hair to test the wear and durability of this new interface to the hair, this sleeve. So that's one way we tested it. We also have a world-class EMC lab for testing all the electronic components and improving those. We do a compliance test with the compliance testing agencies, all of those things.
And we've got thermal cameras, so we can measure the temperature.
Yes.
So we measure temperature as it's being used of the cover here to make sure that it's not getting hot, and the temperature of the hair as before and right after the straightener is used. And what else is interesting about this is this material is very efficient and effective at transferring heat to your hair. So much so that the performance is really good compared to other straighteners, but the hair doesn't get as hot to the touch. So as soon as you use it, your hair is immediately manipulable. I can put my hand on it without waiting for my hair to cool down. We've been testing it in salons around Lexington and in other areas and regionally with great feedback.
That's great. And I mean, 100 miles of hair, that's a lot of hair.
That's a lot of hair.
Hundreds of miles.
Hundreds of miles of hair
right.
is a lot of hair, yes.
Well, it's tested, tried and true, right?
Yes.
That's awesome. Well, thank you so much for coming out. This was a wonderful presentation, and I hope you all learned something about Lexmark and the items that they create. And we'll be moving on to our next exhibitor, Lockheed Martin.
and welcome to E-Day. So we are Lockheed Martin. My name is Auburn Mattingly,
And my name is Haley Mitchell.
and so we work at Lockheed Martin as aeronautical engineers. So what that means is that we analyze things to make sure that they're not going to break. So I actually went to UK. I studied civil engineering, and I graduated in May of 2021 and began working at Lockheed Martin thereafter.
I also went to UK and graduated in May of 2021 and graduated with my degree in materials engineering and began working in June.
Awesome. So today we have a robotic arm presentation for you today, and it's really cool. So Haley, why don't you start with telling us what this is made out of?
So this is made out of 3D printed material. As you can see behind us here, just like these, you can 3D print and make something like this, the robotic arm.
Hey, cool. So can I pick up things with this robotic arm, like these blocks?
Yes, do you want to see how it works?
Let's go into it.
So,
Let's do it.
let's start by explaining the colors you see here. So first, this lever is the blue, so you can follow the fluid back here, and it controls the rotation of the robotic arm. So it's going to move around like this.
That's really cool.
Then you have the up and down, which is this pink color. It's a little bit tricky to see.
Okay, I can see whenever you
Yep.
move this syringe, it's also moving this one.
Yep, and so it goes up and down, and then we have the green that can kind of controls it, the in and
Okay.
out of the arm, and last but not least, my favorite, the orange, that controls the gripper, so you can actually pick something up. So, let's try to get this block
Let's
here
do
on
it.
the front.
This is kind of like the crane game you would do in an
It
arcade.
is. So, I'm moving around, and then I'm going
Right.
to lower it using the pink.
Right, and then that connects to this syringe right here.
Yep, and then rotating it back over just a little bit, and I think I'm ready to go. So let's try to grab
Got to
it.
go down a little
down
bit
a
more.
little bit more.
So we have to use the green one, and then widen out the gripper. They're going to
And
move
let's see.
down, and then close back in on the gripper. There we go.
Oh, I think I've got it. Let's
Apply
see.
some pressure. Oh, you're turning. Look at that. We did a full
I turned
180
the-
with the cube.
Oh,
All right.
And I dropped it. That's okay. Let's try this one.
Cool. So it takes a little bit of practice. It's kind of
Yes,
like
it does.
it feels kind of like an excavator machine, you know, that you would
It
see in a
is.
construction. Yeah.
It's very much like that. Do we want to go ahead and start explaining kind of like how this works?
Yeah. So this is actually powered by water. So I know these are dyed and they're different colors. That's just food coloring. So this is called a hydraulic robotic arm. And why it's called hydraulic is because we have trapped fluid that is under pressure. And so that really has a lot of power to be able to move this arm just like we did here and pick up this cube. And that's powered by hydraulics. Okay, so again, that's trapped fluid under pressure. So we need an incompressible fluid for this to work.
So I'm guessing that water is in an incompressible fluid because it's able to work and pick up this cube.
Right, but something like air is compressible, so it wouldn't work. So we'll start with two different demonstrations. So we have water and we have air. So I'll let you take the water one,
All right,
and then
thank
we'll
you.
start with air. So if I have this air here, I can push, and you see how it's going to go to the other side. But there's a little bit of a lag, okay? But by compressible, I mean that I can squish it. So I can make it smaller and it not take up as much volume. Water, on the other hand, is going to take up the same amount of space, and its density doesn't change, okay? So Haley, why don't you take this end, and then I think we both can push down on it at the same time. So ready? Okay, so we both have pushed down, all right? So we've squished the air, basically. And now whenever I let go, both of us, then it's going to pop back up, showing that we had compressed the air. So ready? 1, 2, 3. There we go. Do you see how it popped right back up? That's because we compressed it. So air is compressible, so it wouldn't work for this because we need an incompressible fluid, meaning that I can't squish it, that it's going to stay the same, the density is the same.
So now we have the water, and we've dyed it blue so it's a little bit easier to see.
All right.
And so now
So
we're going
ha-
to move into this, and you can see that as soon as you push down, the other side, it's
There we
going to
go.
equally go up. So then Auburn can push back down, and you'll see it works both ways, so it'll travel back over, and you can see it moving. But now let's talk about how it's incompressible. So what this means is that if we both push down, you won't
Do you see how it's not moving?
see it moving. It's not going to do anything. It's going to stay stuck.
That's because the density is going to stay constant, which means that it's incompressible, okay? And most liquids are like that. It takes a whole lot to even try to compress it a little bit. So if we let go,
Nothing
it doesn't
happens.
pop up. All right, let's show the air again just to reiterate that.
I think that's super helpful. So let's see here. So looking at the air,
All right, so 1, 2, 3, you can both push down, and we can let go, and it pops,
it pops back up.
showing that it was compressed, okay? So we need that incompressible fluid. So right here, this is our incompressible fluid that's water. So it's going to work just the same way as this because these are just bigger, so it's easier for you to see. These, again, we have one syringe and it's connected to another syringe. All right, and see, as Haley applies the pressure, it's moving it. So that relates to Pascal's law, okay? So what that means is that whenever I apply pressure to an incompressible fluid, it's distributed equally throughout that fluid. So Haley, why don't you explain that a little bit more using our robotic arm?
So what that means is when I am pushing down on any of these levers, you can see that it's equal. So as I push, it's not going to jump and make it move in a different ratio. It's 1 to 1. So if you can see, it's a little bit tricky. When you're moving this fluid, the same amount is going to be traveling like into this tube that I'm pushing out of this tube. So it's going to stay in the same way. And that applies to all of these. Now you may be wondering, how do we see this? Where do we see this in the real world? One of the biggest places is in the excavators, like Auburn said, and the way you can think of that is a really big syringe.
Right.
And
it's actually called a piston that's in an elevator. You know, you have a piston that's pushing down, and if you set it up the right way, by just applying a little bit of force and pressure, you can move really big things like an elevator. And that's because we have different pressures and area and volume, and you can use Bernoulli's principle for that too. So it all just depends on your setup from that. And really, this is powered by the conservation of energy, remember? Because like energy cannot be created or destroyed. That's something that we all know, and I remember learning back in grade school, you all have probably heard that in your science classes. Well, it's true. So whenever we're applying this, the pressure and our force is going all the way through here and coming to the other one, as Haley said. And if you all have any questions, feel free to ask them in the chat, and we'd be happy to answer those. But I think the next thing is, you know, really showing how it works now that we know the principles behind it. So let's explain principles as we do another demonstration.
So let's get it reset up so hopefully we can pick something up without dropping it this time. It's a little bit tricky and takes a little bit of practice. So again, I'm just going to be applying a pressure. It's going to be equal to what I want to see out of it. It's not going to jump and apply a different way. So I'm going to rotate it around and then lowering it back down, hopefully near the cube. And then
you have to go out a little bit.
Going out a little bit more. I think I'm pretty close.
So do you see how she's pulling it? And then see how it's connected this syringe here? So this pressure and force that's being applied here
is equal.
Traveling and going all the way to here. And that's because we have to still have the same size syringes. And so as you can see, it doesn't matter if we have a small syringe or a big syringe like this. We're still going to get the same process going. And there we go.
Look, there we go. Let's see if we can move it around and sit it on the other cube. So we can lower it back down, and maybe it's a little bit easier to see on this pink to see the fluid moving. So if I push down here, you can see it kind of starting to fill down here, which is going to lift it up. So I'm not really going to sit it on the cube, but I can lower it back down, and let's see if it works when I do this. So now, lowering the arm in, and then letting go.
There we go. And so I saw we had a question on the track saying that they didn't know that hydraulic power could power an elevator, but yeah, it can power a lot of things, from construction equipment to the elevator to, you know, the big hydraulic presses that crush cars. I mean, I think that's pretty cool.
I think so too. It's really neat to see how you can put something as simple as a robotic arm into our daily lives and see it all around us in the world.
Right. And then we have another question saying that if you wanted to do something like a robotic arm, would you do robotic or mechanical engineering?
Ooh, that's a good question. I think you could do either, honestly. As long as you kind of know where you want to apply it, getting your degree and spending that time, then you can work in whatever field you want. Like I said, I'm a materials engineer, but I work in the aerospace industry. Yeah. So I do something a little bit different than what I majored in.
Yeah. So really to answer that question, engineering is really broad. So whenever you get an engineering degree, you really get a license to learn, we kind of say. You learn how to problem solve, and you learn the fundamentals of hydraulics, like we just talked about. Or you learn the fundamentals of forces, you know, and thermodynamics, which is a really big word, you know, it has to do with heat and transfer. So you're going to learn all those things, and that allows you to create projects like this because you're relying on those fundamentals. So that's why even your classes now for science and math, why they're so important, because you build upon those. So really, you could do either robotic or mechanical. And like at Lockheed Martin, we have so many different types of engineers. We have materials, we have mechanical, we have aerospace, we have electrical, and then I'm even a civil engineer because I focus more on structures and the structural analysis of things. So we need everyone, you know, and you need all the different types because whenever we do projects, we work together and you have a collaborative team. So that's why it's really important. Yep, and like I said, just throw in some more questions on the chat. I see someone saying they have a question. Feel free to go ahead and ask, and we'll be happy to answer that.
In
And
the meantime, we'll keep showing you how this works and trying to show the travel. So you can keep it moving around and you can keep it.
And something also neat to talk about with this is that water is a low viscosity fluid. Okay, so viscosity, that's a big word.
Yes.
It's a pretty big word. So what that means is that it's going to flow easily, okay?
Yeah.
So you think of whenever you have a glass of water from your faucet. You can easily pour that out, pour it into a new glass. But if we had something like syrup, syrup's kind of sticky, you know? It flows really slow. And that's because it has a high viscosity. So we wouldn't really want something as much like that for this because we're wanting this to flow.
Right.
So,
And you can kind of see that in this, that it's moving pretty easily as I push down. If it was honey or something that had a higher viscosity, you'd have to push a lot harder to get it to move the same amount this easily.
yeah, that's totally correct. And also, we have that, you know, the continuity equation. So what's that saying is that the amount going through here is going to be constant all throughout. And
Right.
so based on the cross-sectional area, you get like different speeds and pressures. So that's how you can set things up to create, you know, a bigger force. And that's how, you know, the hydraulic press and the pistons, that's how they're able to lift such huge amounts of mass or crush a huge car, is because of the engineering behind that and the fundamentals. And that all starts with, you know, what we've shown here with the robotic arm. Cool. All right. So we have a question that says, is there any airplane hydraulics that are connected with hydraulics? So yeah, there are hydraulic systems within airplanes and helicopters. You know, we do aerospace here at Lockheed Martin, and yeah, there are many different hydraulic systems as well. That's why we were saying it's used in everyday life, and there's so many different examples you can find in it. You kind of have to look hard not to find one.
And like Auburn had mentioned, you see this all over in various applications, and you see the smaller being able to do a lot bigger just because of the way that those areas are playing out. And it's really awesome to be able to look at it and see how something as simple and as fun as a robotic arm that you could build at home, if you had a 3D printer, you can use and scale that up to something that's controlling like construction.
Yeah. So we have a question about how long did it take to build? And so first you have to model it. And then after that, then you print it on one of these printers. And it does take a while to print it, you know, because it's going to lay down layer by layer on one of these printers because it has like a bed. And so that is going to take a little while, but it's really fun to watch. And so I think that's really cool. If you ever have a chance to use a 3D printer, be sure to do so, because you're not only going to learn about the modeling aspect, but also how to design it better. And it takes iterations, as they were saying. I know Lexmark earlier in theirs talked about iterating in the design process. Well, you have to do that with this as well, because you have to figure out what works and what doesn't work. And that's part of the problem solving behind engineering.
And I know that the people that were assisting us on this team, a big thanks to John and John who helped us out. It took them about a week to kind of start to get this designed and modeled and then ready to start printing. And as you can see, you can break pieces, so you have to be aware of that as you're working and make sure and be ready to troubleshoot if something goes wrong, because it is powered by syringes. And like on the demonstration pieces, you can pull this out. And if you're doing this on the robotic arm and you have all the water in there, you don't want that to happen, because that could make a little bit of a mess and it won't work. So you have to be a little bit careful and kind of go through that process of learning how to, if it does break, it's okay, just back up and fix it. Thankfully, super glue can kind of help hold some of the pieces together and keep it from moving around when you're trying to build your robotic arm.
Yeah. So we have a question on here about different pressures and like altitude and stuff. So there's different types of energy. You know, you have potential energy, which is based on, you know, like elevation. And you also have kinetic energy. And what it relates all those is Bernoulli's equation. So that's kind of answering your question a little bit more about how that it's still the conservation of energy. So if you want to learn more about that, go check out Bernoulli's equation. All right, cool. Well, is there any way that you can download blueprints for it? I saw that that's another question on there. So there are different places where you can get free, you know, places to print, and they already have the models, like Thingiverse, you know, for 3D printing. So that is somewhere that you can check, but that's always free and stuff. And then you can also design it yourself.
You can design it yourself. There's awesome kits online as well. Like we didn't 3D print our syringes, we ordered those. So you can look online and find kits to kind of build these different types of things. So we made all of our 3D printed components, but we ordered our syringes and the piping that goes with it. So you just have to look on the internet and you can find awesome resources for these 3D printed parts.
Yeah. We have another question on, can you change the size of the claw?
Yes. we decided to stick with this for the demonstration purposes. You would have to go back into your design and redo that and make sure that you would have enough force and power to be able to do that. As you can see, we're using little bitty 3D printed cubes to pick up because we don't have, with these syringes, it doesn't pick up a lot of weight right now. So we would have to change it and maybe use some different size syringes if we wanted to be able to pick up something heavier, or if we wanted to be able to pick up bigger objects, we would need to do that. But we decided for today that this was a pretty awesome size and we could pick up the little cubes for you.
Yeah. So we have another question on how does the robotic arm work? And again, that's Pascal's law. This is powered by hydraulics. So we have trapped fluid under pressure. And that's what's so neat is whenever we have a trapped fluid and you apply pressure to it, how much work you can do.
Right.
As Haley's picking this up right now.
I'm barely pushing down. I know it's a little bit tricky. You can't really tell, but I'm not really pushing this very hard. I'm just kind of using maybe what you'd use to kind of pick up your fork if you were eating lunch or dinner. And that's kind of what it takes to control the 3D printed arm. And that's pretty awesome because we are able to pick up something that's further away.
Yeah, so we have some questions now about what type of 3D printer did you use?
So we used an Ender 3D printer.
Yep. And so then another one is about what is the best material for 3D printing? So you have filament. You can kind of see that on the rings right there on the 3D printer. So that's what the material is that is used to print this.
And if you don't know what filament is a plastic material. So kind of just like you see these cubes are made out of.
Yep. So you can see this, and this is 3D printed as well. It all was. And then we got the syringes, you know, they're not 3D printed, but the crane itself was, and then these blocks as well. So you can really make anything that your heart desires, you know, if you can imagine it and figure out a way to model it, then you can print it. All right. Well, Haley, you got anything else that you would like to tell them besides thank you for joining into E-Day? We enjoyed, you know, answering any of the questions they had and showing them the robotic arm and what we can do with hydraulics.
Yes, thank you for being here today. We really appreciate your time this morning, and we hope you've enjoyed our 3D printed arm.
I know, I always said I needed a helping hand, so here we go.
Thank you.
All right, thank you.
Back to E-Day Live. We are representing an organization here on campus called the Society of Women in Engineering. So my name is Molly. I'm actually studying mechanical engineering.
I'm Megan. I'm studying computer science.
Right, and today we're going to be doing a demonstration. It's going to be a chemical reaction with this right here, which is a red cabbage. So today we're going to be doing a pH demonstration. So red cabbage actually has something in it called anthocyanin, which is a natural pH indicator. And what that is it's kind of what gives it its reddish purplish color. And pH indicators, whenever they're in the presence of an acid or a base, will change colors. And so that's how we know whether or not we're dealing with an acid or a base. this anthocyanin specifically is in a lot of different red fruits you can think of, so like grapes, apples, poppy seeds, things like that. All right, so in order to extract the anthocyanin from the red cabbage, we actually did this at home. You're going to need to boil some water and then cut up your cabbage. Put the cabbage in the boiled water, let it sit for a little bit until that anthocyanin is released, and then you'll get a liquid that just has that pigment in it. And you might be wondering, if the cabbage is purple and that pigment is purple, why our water is blue? It's actually because the groundwater we have here in Kentucky is a little bit basic, and so it's already kind of started to do a chemical reaction here to change that color a little bit. So with that, we're going to go ahead and add our anthocyanin to different household items you'll have and see what color they change to.
Okay, so first up we're going to do it with lemon juice, which is a citric acid, so here, I'll add a little bit more. Creates a nice cool pink color, which is very different from this, and that's just because of the reactions. So the next we have vinegar. And then Alka-Seltzer tablets. It releases some carbon dioxide, so it'll make it more of a true purple color. And then as the tablet dissolves, you'll see it sort of go back to this blue, just because there's less of that carbon dioxide in there, making it more neutral. So then we have bleach, alkaline water, which will be the closest to neutral that we'll get, which is why it's this true blue, which is even a little bit different than this blue here. So then we have baking soda, and now we're getting more into the basic side of the scale, so you'll see the colors start to get a little lighter. Ammonia, which is like a really good cleaning product, so you'll probably have it even if you don't think you do. And then last we got OxyClean. So
Yeah, so what's happening here is, as we're adding the indicator, the different pHs of our solutions are changing the molecule shape of the indicator. And so how light works is it hits different objects and it reflects off of the molecules. And what color light is reflected off of those molecules depends on the shape of the molecule. So when we add the indicator, the different pHs is actually changing the shape of the molecules in each of these solutions. So if you want to talk a little bit more about like the chemistry and pH in general.
So pH itself stands for the percentage of hydrogen. So it's basically just the amount of hydrogen atoms that are in the solution at a given point in time. So if there's more hydrogen atoms, then you're going to be more basic. You're going to be more acidic, which means that your pH is going to be closer to 0. And then if there's less hydrogen atoms, that means you're going to be more basic, and you're going to be higher to that 14. So it's a scale from 0 to 14, with water being the neutral at 7. So anything less than 7 is acidic, anything greater than 7 is basic. Basic things are going to be more slimy and soapy. They're going to be a lot of your cleaning products, whereas acidic things are really sour. They're going to taste better. So like lemons, limes, oranges, those like citric fruits, those are going to be really acidic things.
Mm-hmm. Yep, so something else that's really cool about this indicator is it's actually reversible. So if we wanted to, we could go back and change the pH of anything we've already done, and we'll see a color change back to more towards neutral. So if we were to mix an acid and a base, that's going to kind of neutralize the pH, and it'll go back towards that original blue color. So if you want to pick any, an acid and a base, we'll mix them and see what we get.
Vinegar and ammonia.
Good. Well, we got some concentrated ammonia, it looks like. But you can see a little bit in there where it goes back to blue, and it's definitely closer to blue than it was that green a minute ago, and that is that pH getting a little more neutralized. That's something else. These pHs, they kind of depends based on the concentration of the solution, what the pH is going to be. So most of the items you'll have in your household are going to be a little more diluted just to make them safer for everyday use. So that's why you don't see a crazy expansion of colors, and when we mix that, the ammonia is a little concentrated, so you don't see as blue as it could be. But yeah.
A stronger acid would be more red as opposed to pink, but lemon juice is one of the strongest acids that you'll most likely have access to, without having some crazy certifications.
Yeah,
so.
if you have access to hydrochloric acid, which we don't, unfortunately, you would see a really bright red color on the other end. Also, you might be wondering why the bleach kind of stayed the same color. Because bleach is actually a pretty basic substance. As you know, it's used in cleaning a lot of the times. But bleach is just a really strong solution that actually gets rid of the color pigment altogether. So even though we change the pH of the bleach a little bit, you're not going to see the color change just due to the nature of the chemical. All right, so with that, we're finished with our experiment. We hope you guys get to try this out at home live. It's a really fun one. It turns out really pretty.
Yes.
But if you guys have any questions, feel free to drop them in the chat and we'll go ahead and start answering them for you.
It's fun to kind of just play around with it, especially at home when you can fully mix and see what colors you can create and see if there's any fun, different combinations. Let's see. Is there anything?
All right, so somebody asked a little bit about SWEET. So SWEET is the program that we're here with at UK. It's actually a national organization and we're just part of the UK chapter. So if you want to talk a little more about what SWEET does as a whole.
So SWE stands for the Society of Women in Engineering. So basically it's just a large organization on campus where anyone who's involved in STEM at all can come join us, and we talk a lot about engineering, and we have a lot of community and industry partners that come in and give us topics and teach us about different things. So we've had someone come in and talk about financial wellness and how to budget and get loans and all of that, or someone to come in and kind of share interview tips or professional development. So it's a really cool organization that helps you with your career, but you're also meeting a lot of women in engineering, especially because there's less of us in our classes, so it's nice to have those friends and relationships that you can go to and ask questions about what teachers are the best or what classes would be most beneficial. So it's really just a great way to go out and meet people while also furthering yourself professionally. And we do a lot of fun events as a chapter on campus, but also with the community. So we do volunteering at one of the elementary schools in Lexington. We host prospective students to come and eat lunch with us so that we can answer any questions they have about engineering. And we're hosting a Women in Engineering camp over the summer, which should be really fun, so you can learn a little bit more about what engineering really entails and if it's something you'd want to do.
Yeah.
Anything you have to add?
All right, I don't think so. I think that pretty much sums it up. So I don't know if we see a ton of questions. Oh, someone asked what else we're involved into at UK. We're going to talk about that. So actually, we are in the Innovation Center at UK right now, which is part of our College of Engineering. And Megan and I both are student employees here. So we actually get to show other students how to run all of the machines in this room, whether that be for class projects or if they want to come in and 3D print something on their own. I know I had a friend that just 3D printed a little jewelry holder in here that she only paid a few bucks for, which is super cool. So yeah, it's just a really fun space to be. Other than that, I also work for the Visitor Center, so I actually get to give tours. So if anyone ends up coming to Tour UK, I'll be here doing that. So yeah, lots of fun stuff.
It's a fun place to get involved with. There's always something to do.
Oh yeah, for sure. All right.
Well,
So I think that's pretty much all the questions. Other than that, we encourage you guys to try this at home. Maybe test some different solutions that we didn't, just to see if they're acidic or basic. If you have anything else on hand, any acid or base you have around will work for this experiment other than just the ones we have. But thank you guys for tuning in on E-Day. Hope you guys enjoyed. Hope you guys have a great rest of your E-Day.
have fun with the rest of your day.
See.
Cool.
Okay, so we're at the Women in Engineering Explore Camp at the University of Kentucky, and we've basically been going around to a bunch of different workshops to explore the different types of engineering that UK and other schools have to offer, and hopefully help you decide where you want to go. They're not just learning about the disciplines of engineering, they're actually going to workshops, seeing the hands-on things that engineers here at UK do. And the workshops are all led by the faculty of the College of Engineering.
I think this was a really unique experience, being able to experience all of the disciplines for multiple hours in a day, being there for a whole week learning about engineering, and just kind of getting a taste of what college engineering could be like without it being too overwhelming and all at once like it could be freshman year.
It's very diverse. There's a lot of different opportunities that we can take. There's a lot of different people that we're meeting, and I think they'll all be very beneficial to any field that we'll go into for college.
There is a camp experience. It's just not all like straight lecture, straight education. It's a lot of like also enjoying yourself.
This morning we did like a Zumba video, and it's just kind of something to like get you moving and stuff, because I'm not really a morning person, so it's kind of helpful. You find what you really want to do, because I think deciding your major for college is something that's very sudden at the end of your high school career, and you just have to decide, and it can be scary, and I think this takes a lot of pressure off because you're exposed to so many different areas of interest, and you find ones that you like and you find ones that you don't like, and that's just very important.
I'm glad that I came here and like I got this chance, because it really like brightened up like my future goals and stuff like that.
Kind of tested out how homesick I might be for college and everything, and it was honestly so fun. I met so many great people here. It was just such a great experience, and I recommend that anybody does something like this, especially in engineering, to kind of see all the different disciplines, all the different applications, everything that you can do with it, and really broaden your horizons.
My name's Kay.
And I'm Danielle.
And we're from the Interdisciplinary Engineering Outreach, or IEO for short. And today we have a really cool biochemical and chemical engineering project for y'all.
Yeah, so let's get started. So have any of you guys ever taken medicines before when you're not feeling well, or maybe you're feeling sick? I know I have, and I bet you all have too. We can take medicines for things like a sore throat or a headache or a stomach ache, all kinds of things. Have you ever thought about how those medicines are made? So there's mainly two parts to the process. So the first part of the process is engineers and scientists have to actually come up with new chemical compounds that are good for treating an illness or a sickness or a hurt that you might have. And that's a really complicated part of the process. We're not going to go into that too much today, but we're actually going to talk more about the second part of the process. So that part of the process is figuring out how, once those chemical compounds have been discovered and isolated, we're going to figure out how we can get them into our body and to the right part of our body where they can actually go and do their job that they need to do. So if you think about medicines, a lot of medicines you take are in the form of a pill, right? So all pills pretty much start in your mouth. You put them in your mouth, and then they go into your digestive system and stop somewhere where the medicine absorbs into your body, and that's how it helps you feel better. So how do the different medicines know to stop at different places? How do they know where to go to help your body? So we're going to dig into this a little bit deeper today. So let's see, what's something you might take a pill for, Kay?
Well, yesterday I had a sore throat, and I need to take a cough drop. Does that count?
Yeah. Okay, so a cough drop. So the medicine in a cough drop, you want that to stop in your throat, right? To make your throat feel less scratchy, make it feel better. So when you have a cough drop, it starts in your mouth, obviously, and then it just has to travel a short distance to get to your throat. So for that, we're going to take our Skittle here, and we are going to use this to represent our medicine or our cough drop. And then this cup of water here is going to represent your mouth and your throat, the environment of your mouth and throat. So we're just going to drop this in here real quick. And we're going to wait a couple seconds. And you should see this start dissolving pretty quickly. You're going to start seeing the red color kind of come off of it. And this just shows how quickly, yep, there it is, there's the red, how quickly this medicine can start to dissolve, and then as soon as you swallow, it'll go to your throat and be able to absorb in your throat where it's supposed to go. So that's a pretty simple case. But what about if you need a pill for, I don't know, say a stomach ache? What about that?
That one does get a little more challenging because instead of dissolving in your mouth, it has to make it past your mouth and esophagus, the pharynx and the esophagus right here, that big throat idea, and make it into your stomach, and that's where it dissolves. So it has to make it past, the water simulation and into your stomach. So what engineers actually do is they coat this with like an esoteric kind of coating. You've probably seen it. It's more of a plastic-ish looking, like a Dayquil or NyQuil liquid pill. And what this does, it just protects it from the outside, environment, your mouth, and gets into the stomach. So to replicate this, we have lemon water for our stomach, and we have water for your mouth. And we have this cornstarch. And this is going to go in the water, and this one's going to go in the lemonade. And I'm going to stir it to replicate the stomach churning. And see, if you can look over here, the water one is not dissolving. It looks pretty much still intact, which is the goal. And if you go over here, I'm going to scoop it out for you. You can start to see the red come out, like that's the medicine dissolving, and obviously if it sits there longer, it does dissolve a little bit more.
Yeah, so here our stomach is represented by this lemon water because the lemon juice in this water makes it more acidic because your stomach environment is very acidic compared to the environment of your throat and mouth, which is this water here, which is a lot more basic, kind of like what Sui just talked about. So Kay was also stirring it to represent the churning of the stomach because your stomach acid is constantly moving around. So it's a very different environment, and that's why even the same coating on these pills can make it so that they dissolve in different places, and that's kind of how engineers do it. So inside both these pills there was a Skittle just like the other one, but you can see you get a way different result here than you did with just that plain Skittle that dissolved super quickly. So that's one of the ways that engineers can decide where they want a pill to dissolve and actually make it go there.
So what if I had a headache? Like, where is that supposed to go, and like what environments does it have to go through?
Okay, so a pill for a headache is actually a much more complicated case. So medicines like ibuprofen or aspirin that a lot of times you take for pain, those are actually in a class of medicines called NSAIDs. And those, believe it or not, even if you take it for a headache, it's going to dissolve down in your intestines. So super far away, but once it absorbs in your intestines, it's able to go through your bloodstream, and it actually acts as a blood thinner, and that's how it helps your headache. But it dissolves in your intestine. So in order to get to your intestine, it has to be able to go through your stomach, through your mouth, through your pharynx, through your esophagus, through your stomach, all without dissolving. So that is a big feat here, but we're going to kind of show you how it works. So here we have a Skittle coated in a flour and water mixture. So this is different than what we did before, and it has to make it through the stomach. So again, we have our lemon water here that symbolizes the environment of the stomach, and Kay is mixing it to show us how it's like the churning of the stomach acid. And we're going to see that it really is not going to dissolve. And this coating is what's called an enteric coating. Enteric is a word that talks about something dealing with the intestines. So enteric coatings are things that engineers design that have to make it all the way to the intestines. So this is a big feat. And she's actually going to keep doing this because this is going to take a long time to start to dissolve it all. And I'm going to show you guys how you can do this at home, how you can start to replicate this and experiment with this at home. I'm going to scoot that over there. So here we have a little bit of flour here. So these are a few of the substances you can use to do this experiment at home. We have flour, we have sugar, cornstarch, oil, and then of course our lemon juice and some water here that you can use at home. There are other ingredients you can use too. The main thing is that you need a dry powdery ingredient, so that's these ones over here, and you need some sort of wet ingredient to hold that dry powdery ingredient together. So for mine that I'm going to do right now, I have some flour here. You don't need a ton, just a little bit. And then you're going to put a few drops of your wet ingredient. So I'm going to use water in there. You don't need much. Start with just a little bit of the wet ingredient, and you can always add more if you need it. And then you're going to kind of mix it around, and you're going to mix it until it's kind of a formable Play-Doh-like consistency. You want it to be formable but not sticky. So it can be kind of challenging to find that sweet spot, but that's where you want it to be. And the one constraint on your ingredients, you can think of other ones to use, I'm sure, other than the ones that we have here today,
is that they have to be edible, because if you think about a pill, those are things you're ingesting, you're eating them, they're going into your body. So the ingredients used to make them have to be able to be digested in your body. They can't hurt you, they have to help you. So that's an important thing to remember when you're considering your ingredients here. And all these ingredients that we're using today are not necessarily the same things that engineers would use in real pills. Those coatings are typically more complicated, more complex, but these are good replications that we can use. So once we have our good formable Play-Doh consistency, you're just gonna take the Skittle or your medicine and you're gonna wrap it in your coating. You can tear away some of the excess here. You wanna make sure your coating is pretty thin, because another thing about pills is you've gotta make sure that people can swallow them whole. So they can't be super big. This is probably the maximum amount of big that they could be to reasonably be able to be swallowed whole. But then you have your little pill here and you're ready to test it. So you can test it in water like we did here. You can test it in lemon water to symbolize the acidic environment of the stomach. Another good thing for the stomach is Sprite. That's also pretty acidic if you don't have lemon water. You can test it in other liquids too if you think about it. Some of the ones that Sui talked about might be good to signify different pHs that happen at the different points in your digestive system. So try to, at home, if you want to do this more after this live broadcast ends today, you can do this experiment, try a bunch of different ingredients, see which ones take a long time to dissolve, see which ones take a slow amount of time to dissolve, which ones dissolve in certain liquids and not others. It can be really cool to see if you can get a pill that won't dissolve for 30 minutes. If you're really wanting a challenge, see if you can have one that won't even dissolve overnight. That could be a really big challenge. Another cool thing that sometimes engineers do with these coatings is they put multiple layers of coatings on their pills. So we don't have one here to show you today, but a lot of times engineers will have an outer coating on the pill that dissolves really quickly, and then a more long-lasting coating on the inside that takes a really long time to dissolve. So you could see if you can do that. Do a little bit of cornstarch and then maybe a little bit of flour and water mixture. So you can, all sorts of experiments you can do. Just have fun with it. So now let's go back and check out our flour and water pill over here.
I've been stirring dutifully.
Yes.
And as you can see, still very much intact. This will make it to your intestines. So yeah, that's...
Oh yeah, for sure.
For sure.
Awesome. So it's super cool what engineers can do, and I hope you guys get a chance to experiment with this at home later. So I think we're gonna turn it over and see if you guys have any questions now for us.
We had what things dissolving?
What things dissolving? Okay, so our pills that we have, so to symbolize our pill in the stomach, we had a Skittle covered in a cornstarch and water mixture. This one that we just did for the intestine dissolving, it was a Skittle covered in a flour and water mixture, and then the one for the mouth and throat, it was just a plain Skittle. So the Skittle is like your medicine, and then whatever coating you choose is something that helps it make it to the correct part in the body where you're hoping it'll make it to. And they dissolved in water, and then water with a little bit of lemon juice in it.
Mm-hmm. Any other questions? Not seeing anything else? Mm-mm.
Alrighty. Well, thank you guys so much for joining us today and watching us, and we hope you learned a lot, and you'll be able to try this at home and have some fun with it. So thank you guys so much for watching us.
Have a great day.
Engineering is a major where students have to develop projects, and so students have to have a space where they can come in and act on that. The Innovation Center is set up so the students have the tools that they want to develop anything that they need for their classes or something that they're excited about outside of class. The students have access to 23 printers, a couple SLA printers, which are high resolution, multiple CNC machines and laser cutters, along with other development tools that they might see necessary. The development of the Innovation Center was primarily focused around wanting to be more hands-on with curriculum and trying to find a way where the students can oversee the development of projects of other students. When students come to the lab, we have a system set up for them to get trained on the equipment and then experts in the lab that can help them with their development. Creativity is important because problems come at students from different directions, and so being able to find a solution is not always straightforward. And so being able to look around the corner and find it is a skill that they're going to have to develop. This space helps them be creative because it allows them to have the resources available to them. The fact that all those tools are in one location where a student can come over and develop a 3D print and then integrate that with a part that they're making off the mill allows them to be very adaptable with their design. If they don't know how to solve a problem, they can at least come here and get close and then move further after that.
Wow, what a great first part of E-Day Live. My name is Braden Reichelderfer, and I'm going to be your co-host. We can't wait to show you guys what's next. If you're just now joining us today, we're in the middle of E-Day Live. E-Day, or Engineers Day, is a celebration of curiosity and innovation. For the next 2 hours, we'll be bringing you exhibits, demonstrations, and follow-along activities that will connect you to the world of engineering. This year's virtual event was made possible by the UK College of Engineering and sponsored by Lexmark and Lockheed Martin. Here's a list of the fun exhibits coming up in the second part of the show. The American Institute of Chemical Engineers with Why Do Things Not Mix? UK Biomedical Engineering Society with Terrific Tendons with BMES. University of Kentucky Biosystems and Agricultural Engineering Student Branch with Biosystems Magic, National Society of Black Engineers with Nerf Turret, and a presentation by the American Society of Civil Engineers. Be sure to ask questions and engage with the presenters through the live chat feature. All right, guys, it's time to get started. Up next is the American Institute of Chemical Engineers with Why Do Things Not Mix?
Hi everyone, I'm Jill Steffen and I'm here with the American Society of Chemical Engineers. The chemical engineering industry works to make processes more safe and more cost effective. So we do a lot with reducing waste and making everything safer, which everyone can appreciate. And today we've got a really cool experiment and we're gonna learn why things don't mix. So we have 4 liquids here. I know they're a little bit miscolored, but we'll spell them out. So we have this, it looks a little funky, but this is water, just dyed red. We have some vegetable oil. We have isopropyl alcohol that's dyed green, and then finally we have dish soap. So I want you guys to think, if you're in a room with someone else, discuss what is the difference between this? It could be the color of it, it could be how thick it is. Think about, maybe send in the chat something about the differences between these liquids. Once you've taken a second, we can all see that the color is different, but that's just for the demonstration purposes. The actual difference between it is the density. So do you guys know what density is? If you know, send it in the chat and we can talk about it. I don't know if you've learned this in school, but let's just take a second to think about what density can be. All right. Well, if you guys have been talking about it, density is the mass over volume. So essentially, it's how many atoms are packed into a substance and how dense it is. If you think about a ball of Orbeez, if there's more packed in it, then that means it's more dense. But if there's less and it's more spaced out in the same volume, that's less dense. So here we've got varying densities, and we're going to figure out which one's the most dense and which one's the least dense. And how we're going to do this is add them all together, and they're not going to mix, which I know is crazy because water, these look like they are the same thing. Water and isopropyl alcohol, they look like they're identical, but we're going to do an experiment and see that they don't mix. So the first thing that we're going to do is we're going to take our dish soap. All right, and we're just going to extract it. It's very thick, so this might take a minute. We might just pour this one. Alrighty. Okay, so we've got a whole layer of dish soap, if you can see that. And then the next thing that we're gonna add is water. So we're gonna take our water over here, we're gonna pipette it, and we're going to slowly add it to our mixture. So as you can see, there's a pretty clear defined line between the blue dish soap and the red water. Pretty crazy. You might see this when you're washing dishes, that your soap doesn't always mix with your water, and then this is pretty evident right here. So the next thing we're going to add is our oil. This is not dyed, this is just the color of the water, or of the oil. All right. Perfect. We're going to add this slowly to the container. And as you can see here, another layer has emerged. So now we have a yellow layer, a red layer, and a blue layer, and none of them are mixing. So the final thing we're going to add is our isopropyl alcohol. And you guys might know this because you can use it to clean. You probably have it around your house. So if you wanted to try this experiment, just go and see if you have all of these ingredients. All right, if we can see this, we now have a fourth layer. So you can see the green on top, the yellow under that, the red under that, and then the blue on the bottom. And they're not mixing at all. They're pretty clearly defined. Even if we shake it up a little bit, it'll eventually get back to the original state. So this is super weird. Have you guys ever mixed different liquids together and they haven't mixed? This is forming layers. And all of this is because density. So this is the whole fundamental purpose of why this isn't mixing. And what happens is we put the most dense substance, the soap, on the bottom. And this has a density of 1.06 grams per milliliter. So that's going to be our densest. And then water has a density of 1. So we were able to put that on top, and all those densities are close. Because soap is so much thicker, it was still able to remain unseparated, or separated. Then vegetable oil has a density of 0.93. So we were able to add that on top to create another layer. And finally, we could add our isopropyl alcohol, which has the lightest density of 0.79. So that's why it's able to go on top. And that's just a little intro to chemicals and the interaction between them. Does anyone have any questions? Feel free to add them in the chat, or if we want to talk about density in the chemical engineering world.
Yeah, Jill, great job. That was an awesome experiment. We did have a couple of questions in the chat. Easy Power Training was wondering, what type of oil did you use?
This is just corn oil, so you probably have it in your kitchen cabinet. Can be used to in any cooking, but just your typical corn oil.
Yeah, so could you elaborate on the importance of density in the chemical engineering field?
Yeah, so in chemical engineering, we deal a lot with reactions and mixing different substances. So a lot of our classes deal with reactors, which is just a giant vessel where you add a bunch of things in and you let chemical reactions happen. So you really have to consider density when you think about the order that you add things. For example, if we were to add the water before the soap, they would have mixed and it would have changed the entire dynamic of this system. So considering the order and what materials we're using really is important in the chemical engineering industry.
Wow, that's absolutely crazy to me. So what made you decide that you wanted to be a chemical engineer?
That's a really good question. I knew I wanted to be an engineer because in 8th grade, I went to this conference and they were talking about engineering, and I'd never heard of it, but they just said it's about problem solving and using math and science and just helping people every day. And all 3 of those really clicked for me and really resonated. So since then, I've been taking classes since my 8th grade. I took them all throughout high school, and I knew I wanted to be an engineer, but I wasn't quite sure what kind. But I took freshman year chemistry, absolutely fell in love because this is all chemistry. All the properties that liquids have and how they interact with each other, it's just so interesting and so complex that I knew I wanted to learn more about it. And I've been learning every day. I'm a senior now, and it's just so interesting to get into the world.
Wow. You're making me really jealous. I'm now trying to think maybe, I should have been a chemical engineer myself.
It's not too late.
Yeah. So what would you say has probably been the coolest thing that you've been able to work on at UK through chemical engineering?
Ooh, that's a really hard question. There's so much to get involved in. So actually in the basement of a building right on over there, about a 5-minute walk, there's an entire distillation column. So you can take 2 different substances and separate them based on their boiling point, and then you're able to vaporize one and liquidize it, and then you have 2 separate liquids when you started with one. So we got to run the distillation column, learn the software behind it, and run that, and also understand all of the chemistry behind it and all of the processing techniques in order to run a distillation column. And that's used in the distilling industry, in petroleum, in gas. It's used all over the chemical engineering field. So it was a really great thing to get my hands on and be able to perform.
Cool. Yeah, no, that's awesome. So if you were to have a message for let's say somebody that's still in elementary school, middle school, and they're I'm really interested about chemical engineering or just chemistry in general, and I don't know where to start.
Yeah.
Would you have a recommendation?
I'd say if there's any intro classes, definitely get your hands on it. Joining E-Day is a great start because you're getting early exposure to what all different kinds of engineerings do. And the biggest thing about engineering, and even though you're not chemical, I'm sure you can agree with, is problem solving. And if you see a problem, how do you get to multiple solutions? What's going to be the quickest? What's going to be the fastest? What's going to be the best for everybody? So in everyday life, if you see a problem, just think about it. How am I going to solve this to the best of my ability? And you'll be in great training to be an engineer. I think we might have some questions.
Yeah.
Princess Grace said, what's the difference between density and viscosity? And that's really, really a great question. So density is how packed the liquid is and how the particles are packed into it. So that's more talking about the mass over the volume, whereas viscosity talks about how much a liquid can flow. So that's more about movement, whereas density is just about the mass construct as itself.
Cool. I know I'm kind of putting you on the spot here, but let's say that somebody may be missing like an ingredient or so. Are there any like substitutions that you would have been able to recommend for doing the same experiment that you did?
Yeah, well, I think a great thing is you can do an experiment on the density. If you have a substance that you don't know the density of, try it out and see if it's heavier or lighter. You can just pick 2 liquids and mix them in a specific order, and you'll be able to figure out which one's denser. So even if you don't know what it is, this is a great way to find it out.
Awesome, that's really cool. I'm not sure if you know this answer, but you might. Is density connected to airplanes?
Is density connected to airplane?
Yes.
Density is connected to everything. When you make an airplane, you have to deal with steel and all of the plating. So every material has a density, and that's something you have to consider, especially airplanes fly, obviously. So you have to think about how much weight is going to be in the airplane and if all the different materials that you're going to be using. So density is definitely connected to airplanes. It's connected to everything in this world.
Awesome. And then I got one more question for you here from Philip Stockdale. I do think you know the answer to this one. Do some gas have different densities? Do different gas have different densities?
They do. Although that's harder to demonstrate in an experiment because you can't really show gas as prevalently, but gases definitely do have different densities. Great question.
Cool. Yeah, and I think that's it for the chat. So when it comes to like your experience also at UK, could you like elaborate on like some of like, you know, the communities of chemical engineers and like different things that you can get involved with, specifically with the communities that you're involved with yourself?
Yeah, absolutely. So I'm here representing the American Institute of Chemical Engineers, and that's just the general broad for all chemical engineers. So we have a class where we can learn about different industries and network with industry professionals. But there's also a lot of clubs within that. So we have a solar car and a chemi car. So the solar car, they use solar panels to run an entire car, and they build it, they design it, they code it, and compete in national competitions. And then we also have a chemi car where they create a chemical reaction, which is just mixing 2 things up, and that chemical reaction creates energy that fuels the car. So both of those are great opportunities to get involved in different things, and you get to build an entire car that's super sustainable. And our team won 3rd place this past year.
That's really cool. I didn't know that. That's awesome.
Yeah.
Now, I do have the ultimate question, also from Mr. Philip Stockdale, who wants to know, in your greatest opinion, is water wet?
Is water wet? I'm gonna have to go with an affirmative on that one. I would have to say it is wet. And the density is 1.
There you go. Well, I feel like that answered his question pretty well. All right. So like, is there anything else that like you would want to tell anybody else that might be watching right now?
I would like to say thank you so much for tuning in. I know we have a lot of great experiments lined up, and you get to learn about all the different industries and what makes them different and all of the student orgs. So thanks so much for listening and being interested in STEM. Don't lose that interest. You guys are going to do great things, and thanks for being here today.
Awesome. Thank you for coming. That was awesome.
Hello everybody, my name is Alat Jaludi.
And I'm Trisha Sullivan.
And we're going to be representing the Biomedical Engineering Department. We had a lot of great engineering people come in before us, a lot of great things, and hopefully we can continue the ball rolling with what we have. First, I'm going to start off, what is biomedical engineering? Well, basically, biomedical engineering is trying to solve medical issues using problem-solving techniques and certain technical assistive technology. So that can go from, you know, having a prosthetic leg or a hip implant like one of these versus, you know, Band-Aids are considered a biomedical engineering product. And so today we're going to hopefully show you the examples of how we can imitate the human body in some fun little ways.
All right, so the activity we're presenting today is Terrific Tendons. So we're going to walk you all through an activity where you all can make like a pretend hand, and these strings will represent your tendons, and you can move them, and then your fingers will move in your cardboard hand.
Do a little peace sign with them.
So the things that you're going to need to do this activity, you're going to need like a cereal box, some type of thin cardboard. You're going to need a ruler. You're going to need some straws, yarn. You're going to need beads, and then you're going to need like your scissors, your tape, and a pin.
And so a lot of these should be pretty easy to get at home, but let's say you don't have any sort of like beads or anything like that. A substitution you could use is those same straws that you might be using. If you cut them up a little bit more, you can tie it around. Basically those beads are to make it look nice and just to stop the yarn from going all the way down, so straw will work the same as well if you don't have that.
All right, so the first thing you're going to want to do is you're going to want to take your cereal box and you're going to want to trace your hand on that cereal box and cut it out. And we've already done this in advance just to save time. So this is my little cut out cardboard hand. And then once you've done that, you're going to want to take your straws and you're going to want to cut them into little pieces. The instructions we have online say 1/2 inch. My hands are really small, so I did about 1/4 inch.
And I mean, I even have pretty large hands, and with that, we definitely had to make them smaller. Basically, a good way to measure how big you should do it is if you look at your hand, you can see the little separations between your hands. That's actually going to be where your joints are. Kind of get an idea of where that should be. That's how big your straw cuts should be.
All right, and so once you've got those straw pieces cut, you're going to want to take your pieces and you're going to tape them onto your hand. And basically these are to help separate where the joints are in your hand. Just like this.
No.
And each finger will have 3 of these to represent the 3 joints, and then your thumb will only have 2. So I'm going to go ahead and tape
And while she's doing that, what we're going to do is kind of talk about the science. How does this represent the real hands? And how that would basically go is everyone, if you're watching right now, I want you guys to take a look at your hands. You can kind of see those separations already, where again, between those joints, those little marks, your fingers have these little indentions in your hand that actually signify where your joints are. So obviously, if you bend your finger all the way down, you know, you can see that's one joint. Then you have another joint right there, and then another joint right there. And so with that, that's exactly what we're doing with each of these straws, is we're kind of signifying where each of the joints are. Let's see if we have any questions. Okay, so with that, we definitely kind of get an understanding of how this works. Does anybody know how many bones and joints are in the hand? I'll give you a hint, they're the same number. I'll see if anybody's got to put it in the chat. If no one can figure it out, I will definitely tell you guys. We'll wait a little bit on that. Give it a little bit longer. Basically, while we're waiting to see if anybody knows how many bones and joints are in the hand, we will see, we'll talk about more about how it's structured. So the hand is broken up into 5, I should know this by my head, but 5 different parts. We have the distal phalanges. By the way, I should have mentioned this before. Another name for fingers is phalanges. And so basically, fingers, phalanges is the same thing. So on the top of your hand, these top row, those are called the distal phalanges. The next part, distal meaning the farthest away from the center. The next one is the intermediate phalanges, which basically means right in between. And then you have the primal phalange, which just means the primary side, the center of it all. And then you have the metacarpal, which is the bones that you find in your palm. And then if you look at the very bottom, if you go to your hand and you feel at the bottom of your hand, you can feel it's a little more dense at this little spot right here. That's got to be your carpal bones. And each of those, let's see if anybody got answers. Yes. We got one right answer from Raj, and it is 27. Very close answers, 72, 120. That is a lot. We have that. And basically how it works is each of the top phalanges will have 5, and then we move down, and then, so 5 times 4, which is your 20, so that's got to be from your distal phalange, intermediate phalange, and your primal phalange, and then your metacarpal. All of those have 5 bones, but when you get to the very bottom where your carpal, there's actually 7 individual bones in the hand. But yeah, 27, great job.
All right, so once you've gotten the straws on, they should look like kind of like this. You'll have 3 on your finger. They don't have to be perfectly straight, that's okay. And then what you'll want to do is you'll want to make sure you bend the cardboard space between your straws. And so that represents the joints in your finger. And then once you have that done, you'll want to do this for all your fingers. So you'll have 3 on all your fingers except for your thumb, which will just have 2. And then if you want to, you don't have to. You can add extra straws on the bottom to kind of represent where the different tendons go in the hand, and it just kind of makes it a little bit easier to pull. So once you've got that done, then you'll want to take a bead and you'll want to tie it on the end of a piece of string. These pieces of string represent the tendons in your hand. And then once you have gotten that done, you're going to want to kind of like fish this string through. And one thing to make sure when you're doing the taping the straws on, it's important not to put too much tape, because if you have tape going over the straw, it'll make it difficult for you to thread these strings through because they'll get stuck.
Yeah, definitely try using thinner tapes whenever you're doing it. Another hint, sometimes the straws can get, the yarn's a little hard to put under the straws. So what you can do is you can make yourself a little needle. And so basically if you kind of just cut at an angle, let's see if I can do it here, you can get a thinner strip and it'll kind of help push down the, you gotta be careful again with the things, but you can basically, she'll show you how to do it. Push it down through the straw, that'll definitely help. That's a big thing about engineering as well, is sometimes you have a problem that you weren't anticipating. You know, obviously we're making these little hands and we're cutting stuff, you know, and we found out there's an issue with putting yarn through the straw. As an engineer, the steps you should take is, you know, what's the problem? How can I follow up? How can I follow through to see if I can solve the solution? And when we're working on this, I didn't think of this, she didn't think of this. It was actually another person who was working on this, like, oh, why don't we just use a little needle to send it through? And this way, you all are able to do it at home as well. Now that we're doing that, let's talk about the tendons in your hand. So basically, the reason why we said you can either do 2, 3, or 5, the reason I wanted to do 3 on ours was because they'll kind of connect to the nerves. So you have 3 nerves in your hand. Let's see if there's any questions. Yeah, you have 3 nerves in your hand. You have the ulnar nerve, which controls the pinky and the ring finger. You have the radial nerve, which considers the middle, the tips and the thumb, and then we have the medial nerve, which encompass the middle 2 fingers. And so that's why we kind of said do the 3 for this. And again, obviously it's not going to be anatomically correct because it's a little puppet hand, but if you wanted to get as close as realistic, there is the 3 nerves in your hand. But we're talking about tendons right now. I want everybody to look at their hand, and on the back of their hands, again, you can see this on the little poster that we have. If you kind of like squeeze your hand, you can see these little veins almost. Well, not veins, they're tendons. And how we know they're tendons and not like bones or veins or anything like that is you can actually see the restriction of it, of your hand, which again is why biomedical engineering is so great. We were able to take parts that are just natural in our body and be able to replicate them just through simple mechanical structures. So again, we have this little string that's able to pull down each of these fingers to show exactly how your hand moves in the way. Obviously, there's got to be a lot more complexities, and the nerves inside your brain will send signals to do that instantaneously. But yeah, that's how tendons and nerves work in your hand. Let's see if we have any questions while we're waiting on just kind of you guys to finish it up. And again, ask any questions about biomedical engineering, about the Biomedical Engineering Society, which we're actually representatives of. We have a question from Jessica. What does the Biomedical Engineering Society do? Basically, what the Biomedical Engineering Society does is we're basically throw events to help spread the awareness of certain biomedical engineering issues. We throw little events like pizza parties or Halloween socials as well. But one of the best things we do is we host seminars where we have guest lecturers from all over the place that talk about what specific subject they're involved in. We've had a lot of great speakers and everything. It's a genuinely really cool experience to see how amazingly broad biomedical engineering is. One of the best things about biomedical engineering is you can have sub-focuses. We've had chemical engineers up here. We have electrical, mechanical, and all these things can be applied to biomedical. Like for me, I've done a little more of electrical side and the neuroscience side because that's what I want to do. I want to focus on helping diseases with Alzheimer's and Parkinson's disease. Trisha, what did you want? What's your focus with biomedical?
I did a lot of chemistry and chemical engineering focus within biomedical engineering. I really liked like tissue regeneration. I went to a seminar and they talked about tissue regeneration. And I thought that that was really cool. And that's kind of how I got into biomedical engineering, because I always knew I wanted to do something engineering related, but I also had an interest in the healthcare field, but I don't have a good enough stomach to handle all the stuff that doctors have to handle. So when I started to learn about biomedical engineering and all the different cool things that you can do with that field, I decided like that's what I want to do because it combines two things I'm interested in.
Awesome, yeah. I mean, it's the same here. What's really awesome about biomedical engineering is, you have the impact of someone in the medical field, as well as, some people can't handle the more hands-on stuff. Like personally with me, I love, the medical sides of stuff. And one of the great opportunities that the biomedical engineering department did for me was I got to make a connection with the neuroscience department here at the College of Medicine at the University of Kentucky. And I got to see live brain surgery. And it was awesome. It was so cool to see that hands-on experience and stuff. And this program does so much of that to give you those types of experiences. Well, let's continue on with the last little bit. Once you've kind of got all your straws in and all the all the yarns put through, you should get a little hand like this. Obviously, we went a little bit faster. We do have a little bit of a time constraint. So we posted the link, the brochure for this, which our lovely Jessica Zybart, the Vice President of the Biomedical Engineering Department, made for us. And it kind of tells you that step-by-step of how exactly you're able to make this. And I believe, bring this brightness up. You'll be able to see all the different steps and stuff, and it shows you like a finished product and everything. Now that we've got that, I'll check. If you guys have any questions, I'm gonna start doing some things. Okay. What does a biomedical engineer design, research, or do? It really just depends, The reason why this program is so special, we're actually the only BME program in the country that has a design focus. And so what that basically means is we are more user-ended when it comes to our designs for projects. We kind of take a step to really focus on the ergonomics, the human factor of it all. But yeah, so it can go very broad. I did my neuroscience research on a process called deep brain stimulation, which puts electrodes through the brains that send stimulus, which helps people with Parkinson's and helps settle with tremors. Trisha has done work with NASA with human-powered ventilators and stuff. So, I mean, it's a very broad thing. I know people who have done stuff with prosthetics, which is I'd say that's a pretty common one as well, is working with prosthetics and similar stuff like this, where we're enabling human functions back to people who may not be able to use those in the same way. The next section is, let's see, there's a lot of questions. Oh, I love this. Okay. how much money do you get? That is a great question. That is honestly a great question when it comes to any of the engineering, because it is a concern. Thankfully, with engineering, with biomedical engineering, it's a very broad thing. Once you get your degree, you are pretty set with a career. You can hopefully find one pretty quickly. Now, what exactly you want to do will change everything for you. You know, some people want to focus on research and focus on more of an understanding of, you know, I want to solve this problem and I want to work on research, and you know that doesn't pay that much, but to them the idea of research and getting this problem solved is a lot more, and they'll get grants and stuff to help pay for that. You can go into industry and you can work with different companies like Medtronic and Boston Scientific, and you can get, you know, a basic engineering degree, and you can start off at a pretty good price. Now, to say one specific price is kind of difficult. I mean, I've known biomedical engineers who actually funded about $7 million to the biomedical engineering department to even get the undergraduate, Dr. Joseph Halcombe, which our program is named after. I mean, so you can, it's a very large range. Do you have anything to say? The next question is, let's see. Oh, there's so many. Oh, now I feel bad. I want to answer all these. Let's see. Oh, there's so many. I feel bad. I don't want to miss anybody's questions. Oh, okay, that's a little bit. Stop saying. Okay. When and where did the biomedical area begin? So an exact time frame is hard to say, because biomedical engineering is considered a newer term, but there has always been biomedical engineering devices. The moment that there was a surgical tool to open up your arm or to cut anything to your body for, and has a sterile kind of background, that was considered a biomedical engineering tool. But I mean, it can go all the way back to, you know, I think the first ever medical tool was, I think, in like 600 BC, and I'm not sure exactly on that. What is the science behind air for cracking your knuckles? So that, I'm not too sure about that one either. I do it plenty. It's not a good habit to get into, but it's just releasing pressure. It's not air bubbles, because you can't have really air bubbles in your hand. I saw somebody comment that. But let's see. What does a biomedical engineer design? Do you want to answer that one?
Yeah, I can answer that one. Biomedical engineers can design all kinds of things. You can get into like assistive technology, so designing wheelchairs for people that have certain disabilities, prosthetics for people that maybe have lost a limb. You can get into like making the medical equipment that doctors use in surgeries. You can get into like these are artificial hip joints. This is biomedical engineering. You can design something like this. There's a wide range of things that you can do with biomedical engineering. Anything that relates to people's health that is a device is biomedical engineering. Any other questions?
Yeah, this is one that I'm really interested in. Is how advanced would you say some kind of more advanced full body exosuit is to help people who can't walk, or is that already a real possibility? So the amazing thing about our society right now is technology is out of the walls. There's so many crazy things, and there are full-on exosuits. Now, a lot of these are still, you know, experimental, and none of them are wide produced yet or anything like that, but there is a lot of technologies to allow people to move their foot or be able to walk and stand again. The only issue right now we're walking into is they are very hefty materials. It is a very bulky situation, and one of the things you have to consider, especially making any sort of assistive technology, is you don't want to hinder the way of life of your potential patient. So one of the things we talked about many times is, you know, fundamentally, you want to make sure it works. So efficacy and safety is a big thing. Does it work, and is it safe? But another thing to put in mind is, how does it affect the weight? Because a lot of people don't want a giant, bulky presentation on them to show, oh, I have this sort of disability, or I can't do certain things. And so appearance is a big thing. One of the things we've worked on recently is, you know, there's children's strollers meant for kids with disability that their goal was, of course, they wanted to make sure that the kid was comfortable in the stroller, but they also didn't want it to make it look different. So it looks like any other stroller, and so that's a big thing as well. With exosuits, there's so many things. There's a great TED Talk that talks about the Umwelt idea, and basically it sends electro signals from your brain into the suit that allows people to feel the vibrations of other people's voices, and so basically people can start learning how to hear essentially through vibrations. And there's so many different things, there's so many different research. That's the amazing thing about biomedical engineering. There's so much going on. Honestly, it's really amazing. If you get a chance, just look up, with the exosuits. I guarantee if you looked up any sort of research on it, you'll have a bunch of listings. Let's see how. Blood turns blue. Okay, your body. Oh, we got one question about how blood goes through and is it blue and red sometimes. Deoxygenated blood can have a darker hue, and oxygenated blood has a more reddish hue. That's how it kind of goes. It's not necessarily blue, but the reason we see that is the vein color. Let's see. Erin keeps asking about where and when. I'm not sure where biomedical engineering started, but again, when I believe the first medical tool that was considered for biomedical engineering was in the 600 AC or BC. Let's see. Is it very true, possible, and how advanced? Very. Any other questions? I think that was about it. Hopefully everybody had fun making the little hands. Awesome. Yeah. If you guys have any questions, feel free to ask them now. I will actually do this really quick. Oh, no, it's not in chat. I have to sign into that. Never mind. If you guys have any questions, you are able to actually find more about the Biomedical Engineering Society here on campus. You can look up UKY, BMES, and then you'll have that, and you'll actually have our information as well. So feel free to email us with any questions you guys have that we might have not answered before. Yes, so this is the last one I believe we'll answer, and then we'll hand it over to the wonderful people after us. But yeah, have we found ways to neurologically link someone to control a device yet? Yes, we have. We have actually a few technologies that allow hand movements through nerves in your hand. And again, that would go from the brain to your nerves and everything like that. But it's really awesome. We actually have some of that research going here at UK. I think that was it. Mobility, awesome. Yeah, I think that's it. Thank you guys so much.
Thank you, everybody.
We hope you all enjoyed that.
Bye.
Okay, hi, my name is Allie, and I'm a senior in Biosystems engineering here at the University of Kentucky. My emphasis is in pre-biomedical engineering. So I chose this major because I have always been really interested in the medical field, but I love the engineering and where you take math and science and apply it to real world issues. So biosystems and biomedical engineering was the perfect mesh for me to be able to kind of put those together. And hopefully one day I will be working with medical devices.
And I'm Julia. I'm a junior here at the university, also in Biosystems. My specialization is in food and bioprocessing. So eventually I want to go into the food industry, into food packaging, food processing. Maybe think about, where like the Cheetos that you eat for lunch every day, where they kind of come from. That's kind of where I want to go into in that industry and everything. But I also love Biosystems in the way that it connects me to so many different industries and so many different specializations within all one major that is Biosystems. So we're here to kind of show you guys all a little bit about Biosystems and what we do, but the first thing we kind of want to talk about what Biosystems engineering is. So like I said, we have a bunch of different specializations within Biosystems that all encompasses in the same major. So there are 5 different specializations. The first one is food and bioprocessing. Again, that's what I'm in, so if you're interested in going into the food industry, so maybe thinking about how you package different foods or something like that, you can also go into like biofuels and bioenergy, kind of how to use those different processes and things like that. So that's the first specialization.
So the second one is bioenvironmental. So that prepares engineers to work in the outdoors a lot, work with resource conservation and environmental quality enhancement. So some of the things you might do with that is working on preserving our natural resources, finding better ways to like direct water runoff in big cities, and with that one you're outdoors a lot. So if you're very outdoorsy, that'd be a good one for you.
The third one is going to be controlled environment. So if you're interested in different heating and cooling systems, so think about like air conditioning in different buildings, things like that, that's your controlled environment. So a lot of that goes to greenhouses, different ventilation systems, things like that. So kind of thinking about how the climate affects the inside of different buildings. That's your controlled environment specialization.
So our next one is machine systems, and so that deals with like power sources for power units for tilling and agriculture. So if you're very into like John Deere, you want to ride around on tractors, help design them, that one is a great one for you. It's very focused on all the different types of big machines that you use to like harvest crops and work out in the fields. And we've got some really fun classes for that. I've been in a class for machine systems where I got to drive around a big tractor out back. So that was super fun, and that one is really interesting if you're into that kind of thing.
And our last specialization is going to be pre-professional biosystems. So if you're looking to go into the medical field or some kind of professional field, that's what this specialization would be, kind of similar to what Allie's doing right now.
Yes, so as I said, I'm in the pre-biomedical track, and it's been great being in biosystems because I've been exposed to a wide range of classes, but I'm still able to focus on my biomedical interests, and it's really set me up to solve some real-world problems. So we have some super cool research going on in our department that we're going to talk about at the end after we do our little experiment, but we're going to go ahead and get started on this.
Yeah, so right here you can see some of our experiment that we're going to have set up for you guys. So right here we have 3 standard beakers. There's nothing really too special about them. This first one is going to be all filled with water. You can kind of see here, again, nothing too special about it. And then this one right here is all filled with vegetable oil of the same amount, of the same volume, but again, nothing too special about it right now.
So first we are going to start with this little wooden stick, and we're going to put it in the beaker filled with water, but in the comments we want you guys to guess what is going to happen when we put this in the water, and we're going to take a second and read some of your guesses.
Yeah, so what do you think is going to happen once that wooden rod goes into the beaker? What do you think it'll do, what it'll look like? Any guesses or anything?
Okay, we're going to give a few more seconds for guesses, and then we're just going to go ahead and get it started. Okay, we're going to go ahead and put it in. So we're going to put it first in this beaker just filled with water, and then we're going to show you what happens. Zoom in. So as you can see, it makes the wooden stick look like it is bent when you put it in the water. So the reason that it is bent is because of the refraction of the light. So basically the light is going different distances or going different speeds when it's in the air and when it's in the water, so it causes it to look like it has bent. And light doesn't travel the same speed through all materials. So now we're gonna move it and put it into the vegetable oil. So if anybody has any guesses what it's gonna do when we put it into the vegetable oil, if you wanna go ahead and put those in, and then we'll do that.
Oh, let's see, some people saying the rod becomes wet. It does. It will look magnified, yeah, a little bit.
Red.
Somebody said, I think it will fizz up.
Fizz up?
Interesting.
That would have been fun. Let's see. Okay. Okay, I think we're going to go ahead and put it in the vegetable oil.
Okay, awesome, perfect. So you can kind of see in the vegetable oil, the wooden rod looks a little bit more bent than it did in the water. And again, that's because of all the light refraction. And since oil is different than water, it'll look a little bit more bent.
So now we're going to try this again, but instead of using this wooden stick, we're going to use our little glass tube. So again, we're going to put it in the water first. So after seeing what happens to the wooden stick, if you guys want to put in the comments what you think is going to happen to the tube, you can go ahead and put that in. Let's see. I don't know if we have any guesses for this yet. Someone said that they thought that it wouldn't get bent in the vegetable oil. I think that was for the wooden stick. So like we said, just because the light travels a different speed, it actually ends up getting more bent in the vegetable oil. And do we have any guesses for the glass tube? I think it takes a second for them to load. Let's see. The rod will start the process of nuclear fission. Okay, that's a big thing. I don't think that'll quite happen, but we'll see. Same light refraction. Okay, so we've got a guess for that. Okay, nice. So we're gonna go ahead and put this into the water. And you can see again, let's see here, that it does still get a little bit bent. There, you can see it at a good angle there. It kind of slides it over to the side almost. So that is what happens in the water, and now we're gonna test what happens when we put it into the vegetable oil and then fill it with vegetable oil. So go ahead and put your guesses for what's gonna happen when we put it in the vegetable oil and then when we fill it up with vegetable oil.
See, people saying it won't get bent. It won't bend because it's clear. All great guesses.
And just to review, it did bend in the water, so we did still have the bend in the water. So what do we think is gonna happen in the oil when it's filled with oil? Okay, so we're gonna go ahead and do it. Our biggest guess is that it will not bend because it's clear. So we're gonna go ahead and fill it up and show you what happens. Okay, everybody see that? Magic!
I mean, so you can see that it disappeared once it was filled, and that you can see is a little bit because the glass is traveling at the light is traveling at the same speed as the vegetable oil and in the glass as well. So once you put the vegetable oil inside of that glass tube, it all disappeared and looked like you couldn't even see it.
Okay. And now we've got this beaker that has some water in it and some oil in it. So if everybody wants to put their guess as to what's going to happen when we put the wooden stick in, you can do that now in the comments.
And you can see here too, in this beaker we have the water and the vegetable oil. They are separated so they won't mix. So you can see the water is going to be at the bottom and the vegetable oil is at the top. So yeah, we'll put the wooden rod in, and then we'll also put this test tube in again. So if you guys have any guesses about what will happen to either of those, put your guesses in the comments. Invisible.
Let's see, we got some comments that they don't see it and it was invisible in the oil. Yes. It's like magic.
Awesome. Cool. Okay, I think we can
Okay, we'll go ahead and go. So we're going to put the wooden stick in first. Hold it down a little bit.
Again, you can kind of see that it's bent where it's the water and the vegetable oil meet, but then once at the top, you can see that it's not as bent a little bit. So you can kind of see that a little bit.
Okay, perfect. And now we're going to do it again with our little glass tube filled with the vegetable oil.
Awesome. So you see it kind of disappears when it's in that layer of the vegetable oil, but then it'll reappear again when it's in the water. So it looks like it kind of disappears, goes away, but then it reveals itself again once it goes in the water. So as you can see from our demonstration, there are some things that you can hide and some things that you simply can't. So we can relate this to a lot of problems that bioenvironmental engineers and biosystems engineers face in general on every day what they're doing. An example of this is going to be climate change. So I'm sure everybody hears a lot about climate change and the issue that's going on. Bioenvironmental engineers are actively trying to research into this issue, fix this problem. There has been issues in the past where we don't have the resources and the research that we need to solve the issues that we are facing today, but right now we're kind of uncovering all of those resources that we see to fix the issue that is today, so kind of like our demonstration here.
So another example is feeding the world's population. So the world population is expected to hit 11 billion by the year 2100, which is a ton of people. That is a lot of mouths to feed. And currently we just do not produce enough food to be able to sustain a population of that size. And that's another one of those problems where it's not necessarily something you'll see like with your eyes physically, but we know that there's not enough food for everyone to survive in like a healthy way on the planet. So that is something that biosystems and environmental engineers are trying to solve through maybe like more sustainable ways to grow crops, ways to like increase crop yield, things like that. And then some of the other issues that are maybe harder to see with your eyes are pesticides, pollution, and then finding ways to have alternative fuels and then protect natural lands and resources. So like we said, these issues are a little bit harder to see and sometimes are easily overlooked. You might not even be able to see them at all. Just like this tube that we've had hidden in the oil the entire time, and you haven't been able to see it, just like some of these issues. So some of the research that we are doing in our department to help solve these issues include looking at robotics, sustainability, and then animal science. But we all look at it from like an agricultural and environmental standpoint, so looking at the food, water, and energy that is required for these solutions. But we've got lots of different projects here. You can look on the Biosystems Engineering website at UK, and it should have a list of all the different research we're doing. And if you come here, some of that is research that you can maybe help in.
Awesome. Well, thank you guys all for tuning in. We want to thank Gary Lopez for sponsoring our project and to the Biosystems student branch for our exhibit today. But if you guys have any questions, feel free to reach out to us online, on social media, and everything like that.
Yeah. And we can take some questions in the chat if you guys have any questions about the experiment or just about biosystems engineering in general, and we can take a couple minutes or so to answer those real quick.
I think everyone liked it.
Yeah, everyone said it was cool. A magic trick.
You can do this at home as well if you have Pyrex glass and Pyrex test tube like this. So if you want to check it out for yourself, you're also more than welcome to do that at home.
Yes. And also let us know if you saw our hidden tube or not. Maybe you have better eyesight than most people, but it was hidden in there the entire time.
Awesome. Yeah. Well, thank you all again for tuning in. Again, feel free to ask us any questions. But yeah.
Yeah, we got, this is pretty dope. Yes, it is. Just like our major, Biosystems is pretty dope. Let's see. Someone said hi. Hi, Philip. Hope you enjoyed our magic show. Let's see. Any questions?
So cool.
Wait a second. Okay, let's see. What happens if you move the tube in the oil from Philip? So I think he's meaning the one in here. So you can kind of see, let me find it. It's kind of hard to see in person too. So when you move it, you still can't really see it. You can a little bit see the outline just from the light in here that's shining on it. But because it's filled with that vegetable oil and light travels at the same speed through vegetable oil and glass, it still kind of keeps it invisible. And you can see that's the one that we've had hidden, and our extra one was over here. Want to take the next question?
Yeah, someone said, would the same thing happen if it was filled with water and water? So no, it wouldn't happen because, again, the light will travel at the same speed in the glass and the vegetable oil, but not necessarily in the water. So if you fill it with water and put it in that beaker, it'll all be the same. So you should still see it, but again, it'll just disappear in that oil.
Let's see. Didn't even know that was possible. Yeah, it's pretty cool. So like we said, it's because of the speed of light and how it travels. Since it travels the same through the glass and the oil, that's why it makes it invisible. And let's see if there's any others. Okay, I think that's it. So thank you guys so much for tuning in, like we said, and if you ever have any questions about Biosystems, feel free to reach out. Bye.
Bye.
Alright, so we're at the Women in Engineering Explore Camp at the University of Kentucky, and we've basically been going around to a bunch of different workshops to explore the different types of engineering that UK and other schools have to offer, and hopefully help you decide where you want to go.
They're not just learning about the disciplines of engineering, they're actually going to workshops, seeing the hands-on things that engineers here at UK do. And the workshops are all led by the faculty of the College of Engineering.
I think this was a really unique experience, being able to experience all of the disciplines for multiple hours in a day, being there for a whole week learning about engineering, and just kind of getting a taste of what college engineering could be like without it being too overwhelming and all at once like it could be freshman year.
It's very diverse. There's a lot of different opportunities that we can take. There's a lot of different people that we're meeting, and I think they'll all be very beneficial to any field that we'll go into for college.
There is a camp experience. It's just not all straight lecture, straight education. It's a lot of also enjoying yourself.
This morning we did a Zumba video, and it's just kind of something to get you moving and stuff, because I'm not really a morning person, so it's kind of helpful.
You find what you really want to do, because I think deciding your major for college is something that's very sudden at the end of your high school career, and you just have to decide, and it can be scary, and I think this takes a lot of pressure off because you're exposed to so many different areas of interest, and you find ones that you like and you find ones that you don't like, and that's just very important.
I'm glad that I came here and I got this chance, because it really brightened up my future goals and stuff like that.
Kind of tested out how homesick I might be for college and everything, and it was honestly so fun. I met so many great people here. It was just such a great experience, and I recommend that anybody does something like this, especially in engineering, to kind of see all the different disciplines, all the different applications, everything that you can do with it, and really broaden your horizons.
Engineering is a major where students have to develop projects, and so students have to have a space where they can come in and act on that. The Innovation Center is set up so the students have the tools that they want to develop anything that they need for their classes or something that they're excited about outside of class. The students have access to 23D printers, a couple SLA printers, which are high resolution, multiple CNC machines and laser cutters, along with other development tools that they might see necessary. The development of the Innovation Center was primarily focused around wanting to be more hands-on with curriculum and trying to find a way where the students can oversee the development of projects of other students. When students come to the lab, we have a system set up for them to get trained on the equipment, and then experts in the lab that can help them with their development. Creativity is important because problems come at students from different directions, and so being able to find a solution is not always straightforward. And so being able to look around the corner and find it is a skill that they're going to have to develop. This space helps them be creative because it allows them to have the resources available to them. The fact that all those tools are in one location where a student can come over and develop a 3D print and then integrate that with a part that they're making off the mill allows them to be very adaptable with their design. If they don't know how to solve a problem, they can at least come here and get close and then move further after that.
Hey everybody, my name is Joseph Guthrie. I'm with the American Society of Civil Engineers, student chapter here at the University of Kentucky. I'm a senior civil engineering student here at UK.
My name is Dean Weber. I'm a civil engineering student as well here, and my focus is in structural engineering.
My name is Devin Willett. I'm also a student here at University of Kentucky. I'm also in ASCE, and my focus is more transportation and construction.
So today we're going to be talking to you guys about concrete. Basically the origins of concrete, what concrete is made out of, and at the end of this presentation, you'll probably be able to, if you can get a hold of some Portland cement, you'll be able to go make a concrete sandcastle in your backyard if you want to. So at the beginning of time, we made houses and structures out of stone and timber. Basically, it was whatever materials we had laying around. About 2,000 years ago or so, the Romans figured out that you could actually mix in volcanic ash with sand and gravel and get a really hard material. That's what we know today as concrete. The three basic materials of concrete are Portland cement, fine aggregate, which is typically a sand, and then you have coarse aggregate, which is typically a gravel. You mix all these materials together and you add water, and over time a chemical reaction occurs with the magic sauce, which is basically the Portland cement, where everything gets really hard. So this is a piece of concrete that you can see we've cut in a cross section, and basically you have the larger pieces of aggregate, and then the other void spaces are filled with a combination of cement and sand. And what happens to make this hard, when the water reacts with the Portland cement, it starts to form crystals over time. Those crystals grow and they build a compressive strength within the material that causes the concrete to be really hard. So another thing that we do to determine the strength of concrete, because today we design these materials in such a manner that you can build giant skyscrapers. And so we have to know specifically exactly what the strength of this material is. In order to do that, we'll do test materials, test cylinders like this, and then we'll actually put them in a giant hydraulic press and crush them and see how much force it takes. So typically concrete is around 4,000 to 5,000 psi, but we have special mixtures that we can get up to 10 and 12,000 psi, which means for every square inch you can hold 10 to 12,000 pounds. So basically this is the example of a crushed cylinder that we used, and you can see basically it's sheared off from the compressive force of that hydraulic ram. Another thing that we use in concrete in order to make it extra strong and to span long distances, we'll actually put steel rebar inside of the concrete. So this is actually an epoxy coated rebar, because water will still pass through the porous concrete material, and it will cause regular steel to erode and corrode rather, and it will expand and bust off, and it'll make the concrete fall apart. So we put this epoxy coating on there to protect it from the water elements. See, it has these ridges in there so that the concrete, when it's wet and we pour it over the rebar, it will actually bond really well. Steel is incredibly good under tension, and concrete is incredibly good under compression. So we put these two materials together and you can make skyscrapers. It's incredible. So at this point we're going to show you guys how to mix up a little bit of concrete.
And we have a question in the chat about how the steel corrodes in the concrete. So if you've ever seen anything that's rusty, the metal, when it's exposed to water and oxygen, will rust. Anything that's iron-based, which is steel is, will rust. And so the water can penetrate into the concrete and get that metal, that reinforcement wet, and then over time it will rust, and that rust is will expand because of the chemical reaction, and that will break the concrete. So that was a good question in the chat.
Yeah, pretty much all concrete is a porous material. Even though like this looks like it's pretty solid, there's tiny little microscopic ways that over time, you think about how long a building sits outside, it's forever basically. Water will get on the concrete and will slowly start to get inside of it, and typically you'll have pieces of steel in different configurations, and the water will actually attack it, like Dean said, and make it corrode.
All right, so to mix this concrete, we're going to do 1 scoop of Portland cement. So we're going to get that in here. Then we're going to do 2 parts of fine aggregate or sand. And then we're going to do 3 parts of the coarse aggregate. Just kind of like gravel. And then kind of our last part here, we're going to put some water in there. We're not really sure how much to add in here, but just going to kind of wing it here.
So typically when we would design an engineering concrete mix, we would know specifically exactly all of the parts and pieces by mass and by volume, how much to add in there. And we have really specific variables on the water to cement ratio to design the strength of the concrete.
I know that this really isn't kind of hardening, but when you design this, we'll have, of course, more than this, so we can have like a cubic yard. And when this all mixes, this will kind of make like a, it'll kind of be, we call it like mud in the concrete industry. And then when we put it in place, we would like vibrate it with a vibrator, and that kind of sets it down. Then over time, we put water on our burlap, which is kind of like a cover to keep the moisture in. And then it'll harden over time, like if you're going over a bridge, there's like a concrete deck. That's kind of like it'll harden like that, and it'll be regular concrete. And then the steel in here represents the reinforcement to keep it with strength.
Yeah. So typically you'll see big concrete trucks driving up and down the highway from time to time. It just looks like a truck that has a giant tank. You'll see them spinning. That spinning action is actually mixing the concrete together as it's driving down the road. We have giant batch plants all over the United States that makes up concrete for construction projects, bridges, dams, buildings, all over the world. And they'll actually mix the concrete up to some degree at the plant, put it in the truck, and that truck will be continuously mixing it as you drive out to the job site. The construction workers will be ready for the concrete when it gets there, and they'll be able to pour it into forms for all the different magical shapes that we put together with buildings. One of the other crazy things about concrete that we're able to control is the specific gravity or the mass of the concrete. So most concrete, generally speaking, is around 155 pounds for every cubic foot. That's 12 inches by 12 inches by 12 inches. So what we're able to do is design a mixture that's incredibly lightweight. We adjust the mixtures of the coarse aggregate and fine aggregate, and we can actually replace those with little perlite or foam balls, manufactured spheres that weigh incredibly less than the coarse aggregate gravel that we use. So much so that we can have some concrete that is actually a little bit heavier than water, so it sinks. And then we have other concrete that we design that is so lightweight, but it's still very strong, that it actually floats. One of the other applications that we use with this incredible lightweight concrete is we actually build a canoe. One of the things we do here at UK is we compete in what's known as the concrete canoe competition. This is a competition that's nationwide, and it's one of the very few ways that we have the opportunity to compete as engineering students with other schools. So as Devin said earlier, we use the steel rebar to help strengthen the beams and bridges and dams and stuff like that. We will actually use carbon fiber mesh, which is what these things are. It's incredibly lightweight, but much, much stronger than steel. We will do layers of concrete and mesh, concrete, mesh, and a last layer of concrete in order to make an incredibly strong but extremely lightweight canoe. We'll actually take this canoe and race it at competitions. There's a regional competition and a national competition. We have students that are able to get in the canoes and race other schools. This is about as close as we come to like an NCAA national championship for engineering students. So it's pretty exciting, pretty cool. This is just a cross section that we made, and you can kind of see the formwork that we would use to shape and mold the concrete canoe. I think we have a picture of our big canoe. So the big canoe that we made, it weighs about 200 pounds, and it actually floats really well. So as you can see with the concrete we had in the tank earlier, even when you submerge the canoe all the way underwater, it's such lightweight materials that it actually floats and pops back up to the surface. So that's pretty much some of the more fun things that we do here at UK.
Someone had a question in the chat, again, asking how the concrete floats. So if you can think about dirt, right? Dirt you would find out in your backyard. Dirt is just basically crushed up rock. And if you put that in water, obviously it doesn't float. But you think about some other things that do float, like wood or other materials like that. We can find special materials that are just as strong as traditional rock, but also float. And so we use those instead of the rock and the concrete, and that makes it so light that it can float in water.
Yeah, so basically 1 cubic foot of water weighs 62.4 pounds. So we know that, and we go into a laboratory, we do lots of tests with our concrete mixtures, and we can actually design in a laboratory concrete that weighs less than 62.4 pounds. So anything that's less weight than water will float. So for example, this concrete block is 70 pounds per cubic foot. So obviously it sinks. And even though this is much smaller than the mass of this thing, this is about 40 pounds per cubic foot. So it's almost halfway out of the water. So that's the kind of principles that we use in order to make our whole canoe. Got any other questions?
Nope, no more questions.
Yeah. So other things that you can do with civil engineering, obviously, in addition to making concrete canoes, I spent the last 10 years working as a commercial diver. And so I've done a lot of underwater bridge inspections. All the bridges in the United States have to be inspected every year by civil engineers. So I would help with that and do construction work. So another thing.
So I worked with the Kentucky Department of Transportation. So your roads that you drive on every day, we have a part in that. So I've repaired. So we have cracks in the road, and we've completely torn up a road and repaired it. And also I inspected a bridge. So this bridge was about 600 foot long. So we would go up there and we would make sure it was good and everything. And also we would watch the construction workers put in the rebar and also put in the concrete for the deck. And it was a good experience. So civil engineering, think of just not only concrete or buildings, you can do a lot of things like water resources or environmental engineering. So it's just more than one aspect of like concrete. You can do a lot more with civil engineering. Then Dean, you want to talk about your experience?
Yeah, I can. There was also a question in the chat about somebody asked, would this concrete mix be useful in building houses near areas with flooding, where flooding occurs? So that's a good question. Usually we don't want our houses to float because that can cause problems. Because as you can imagine, your house could float away and end up in somebody else's yard, and that would be kind of a disaster. So it's a good idea, but no, we wouldn't use floating concrete in house design. Usually the heavier the houses are, the better, because that way if there's a hurricane or strong winds or a tornado, they won't get picked up and moved somewhere else. So with houses, it's important that the houses are pretty heavy, that they stay on the ground. That's the best place for your house to be, but that's definitely a good idea.
Any other questions?
Somebody also asked, what's the difference between a civil engineer that works on bridges and an architect that also works on bridges? So that's a great question. There's a couple of big differences between a civil engineer and an architect. The biggest one is what they focus on. So civil engineers will focus more on the technical, the math side of things, making sure everything is safe, making sure everything doesn't collapse. There's a little more physics involved to make sure that everything is safe. An architect usually works more on the aesthetic or the design part of the bridges. So they want to make sure everything looks nice, everything is usable for the people that use the facilities. That it's not an eyesore. So the biggest difference is civil engineers are more technical, they do more math and physics, and architects are more design-based. They care more about how things look.
Anything else?
No, that's all the questions for right now. So I think that about wraps it up.
Yeah.
So thank you everyone for watching.
Yeah.
And hopefully you enjoyed this presentation.
Yeah.
Hi everyone. My name is Jachi Mike Onoha, short form Jachi, and I'm here with my friend
Bryce Grant.
And we are representing the National Society of Black Engineers. Welcome to E-Day, and today we are presenting our Nerf torrent. So I'll give you guys a brief rundown of what we do at NSB, and then I will talk about the project. So the National Society of Black Engineers is a minority student organization here on campus. We welcome all majors, and we host a lot of events, both career-driven and for fun, for our students to, get to relax and improve themselves professionally and succeed academically. We host study sessions, and we also host career talks and invite other engineers to come and speak with our members, to help us learn what it's like to work in the industry. I'm currently a senior in computer engineering, and it's been an amazing experience since I've been here at UK. And I've learned so much that I was able to work with my friends to create this Nerf torrent. So this Nerf torrent was inspired by a whole bunch of YouTube videos that we've seen, and ways we wanted to just make something that was very interdisciplinary in engineering. It has computer science, computer engineering, mechanical engineering, and even some architecture involved in the design and building of this prototype.
Yeah, so essentially what we have here is this Nerf turret, and we have these two motors right here. Here's the motor to move it in the y-axis, and then we have a motor right here which rotates the base. And we have a servo motor right here which was hypothetically going to flip the switch, but unfortunately we weren't able to actually integrate it within the design. But we are powering these motors through a AC adapter right here, which provides 12 volts to the entire motor circuit. And then we have this joystick, which is connecting the Arduino, which is our microcontroller, with the rest of the circuit, which allows us to actually control the turret. So that allows us to move it in the y-axis. And although it's a little bit finicky, this allows us to move it in the x-axis. But really, we learned a lot doing this. And I think one of the biggest things we learned is that engineering is not perfect. You're always going to make mistakes. And although we wanted this to have like a full range of motion, as you see right now, it's not turning all that great. But that's one of the things that we're learning, and we definitely plan on making greater strides in the future. And definitely, like, this is just a prototype, but it's been amazing working with Jachi and one of our other members, Jesse, doing this, and it's been a lot of fun.
So I'm pretty sure everyone is pretty excited to see how this thing works. So let's give it a little bit of a test run, shall we?
All right.
So we replaced the rev motor switch, so the switch that makes the flywheel spin, with this. So let's load our little pack of darts. We don't have that many. So we load that in, set and ready. And once I put this together, you're going to hear a rev. So let's give it a little aim.
Where are we aiming to?
Try and get a bit up, just a bit. That's down. A bit up.
All right.
I'll just flip it.
Should we use this?
Oh, let's try and use this. Let's see if this will.
Other way.
Sorry, it's the other way. So give it a push. Hey!
I think it jams.
Yeah. So.
But it worked.
It worked. So that was our final prototype. So that is our prototype, and you can always take it out, and we might actually be able to try it again.
Yeah.
So, just because the fans want to see more, let's give them more. So let's try this again. So let's try and aim a bit down now. All right. Oh, that was nice. Let's give it another one. Oh, sorry, let's give it another go. I think it jammed again. But yeah. So this was a really cool project that we really enjoyed working on, and we definitely plan to keep improving it, and maybe even add something crazy like facial detection, so you can track people and all that. But yeah, we hope you guys really enjoyed it, and we hope this has inspired you, 1, to look more into engineering, 2, to not be afraid to make mistakes, and 3, to work on something cool with your friends, because we had a lot of fun working on this together. So I'm Jachi, and
I'm Bryce again.
we are Nesby.
Are there any questions from the chat?
Someone called it advanced military technology. I agree with that. I actually agree with that. Turrets and cannons. Well, yeah, I see a lot of people saying they have Nerf turrets at home. I mean, you can piece yours together and try this out. There are so many cool tutorials online, and you know, it's just like you can also use other pieces of plastic, or you can, you know, be a bit creative, be a bit innovative, and get your own thing running together. So yeah, I don't think we have that many more questions in the chat.
Well, thank you.
Thanks, guys. Have a great E-Day.
Well, thank you so much for joining us at this year's E-Day Live. I hope that you learned something new and that your interest is piqued. If you have any more questions about engineering or the University of Kentucky College of Engineering specifically, please feel free to look at www.engr.uky.edu.
And I just wanted to give one last big thank you to our sponsors, being Lexmark and Lockheed Martin. We couldn't have done this without all of your support. Thank you guys all for joining us for this year's E-Day Live. I hope you enjoyed it.